Hello, this is Todd Booth. I'll be giving you a presentation on Chapter 4, Key Distribution and User Authentication. So it's in this chapter that we're going to cover two important related concepts. The first is the complex topic of cryptographic key distribution. That'd be like password distribution. It involves cryptographic protocol and management considerations. And it's this chapter that will give you a feel for the issues involved with and provide you with various aspects of the key management and distribution. So it's key management is just management of passwords like shared passwords or other types of passwords. And we call it management, which is to keep track of them, where they are, not lose them. How do we pass them among the parties so the hackers can't get them in between, etc. So in this chapter, we're also going to examine some of the authentication functions that have been developed for network-based user authentication. And back in the beginning, we didn't have network-based user authentication. When the computers first came out, the users were physically present at the computer, and then they put in their name and password or whatever, and they could get in. But with network-based authentication, it's a lot harder to know who is on the other side of that network connection. And is some attacker manipulating the data before it gets to us? So we'll talk about how to do network-based user authentication, which is quite different. So it's in this chapter we also have a detailed discussion of one of the earliest and most widely used key distribution and user authentication services, Kerberos. And that's also used in Windows, just so you know. So it is really popular. It's popular in a lot of different operating systems, but Microsoft uses it also. And then we're going to look at key distribution schemes that rely on asymmetric encryption. And that's very interesting. We have these conventional encryption keys, otherwise known as symmetric encryption keys, and we want to pass them around in a secure way. And what we're going to do is we're going to show you how to use asymmetric encryption to pass the symmetric encryption keys around in a safe way. Then we're going to talk about X.509. Now I know you've seen so many different standard numbers. You're probably sick of them, but this X.509 is with regard to certificates and public key infrastructure, and it is so popular. It's used just all the time. They have a couple of versions, but and that is a way that we can ensure the identity of the person. We'll have a much higher confidence by using that protocol. And finally, we have the concept of federated identity management. And what that is do you really want to have 100 user IDs and passwords to go onto different systems? Well, maybe you do today, but the idea is if you work in a company, you might have a bunch of different systems and services you want to use, and we can use this federated identity so that if you have a logon at your company and you're doing some work at your partner's company, some partner of your company, that you can use your own credentials, you can authenticate through your own organization, and then that gives you access to the partner company you're working with. And I think as time goes on, we're going to see a lot more of that, so that when you go to 100 websites, you don't have 100 user ID passwords. Okay, we have an opening quote again. I'll let you just read this. You can pause, of course, and continue. Okay, now we're going to talk about symmetric key distribution using symmetric encryption. Symmetric means conventional encryption. And in conventional encryption, we have a shared key. It's shared between the sender and receiver, and we need some way to move the key around in a safe manner. And that's what we're referring to as key distribution. So for this symmetric encryption to work, the two parties in an exchange must share the same secret key. And we need to protect that key from access by others. And we need to make frequent key changes. We don't want to use the same key forever. And if we make more key changes, then it limits the amount of data compromised if the key is lost. So the strength of any cryptographic system rests with the key distribution technique, how we can move the key around safely. And it's just delivering the key between the parties who want to exchange data privately. Now, the key distribution, we have a whole bunch of different ways to do it. For example, if two parties A and B, like between you and a friend, you have the following options. One, a key could be selected by you, and then you could physically deliver it to your friend. Or maybe a third party could select the key and give it physically to both of you. And of course, you'd have to trust the third party. Now, if both of you have previously and recently used a key, one of you could transmit the new key to the other using the old key to encrypt the new key. And if both of you have an encrypted connection via the network to a third party, then that third party could deliver a key over the encrypted links to both of you. Now, the problems with the first two include a manual delivery of a key. So that's a physical delivery. So with physical delivery or manual, it's safe, but it has some other issues. We can't do things fast, so that's a problem. There might be a couple of applications where that might be okay, but we also want to have a solution where we can share the key very quickly through the network. Now, option 3 is a possibility for link encryption or end-to-end encryption. But think about this. If the attacker gains access to one key, like the initial key, they can use that to decrypt the session where the next key was shared, and then they'll have access to that key, etc., etc. So that's got some problems. And then we have option 4. And in option 4, we have two types of keys. We have a session key, and during the session, the two end systems will use that session key to perform the encryption and decryption. And after the session, they take that key and they destroy it. They don't use it anymore. And there's also a permanent key. And this is interesting. The permanent key is used between the entities to distribute the session keys. The permanent key is not actually used for any sessions. So what we need to do is find some way with this option 4, the permanent key, is to have what's called a key distribution center. We want to have the logic and the systems in place to have a way to distribute these keys, the session keys. And this key distribution center, KDC, will determine which systems are allowed to communicate with each other. And when the permission is granted, then the key distribution center will give them a one-time, meaning they can only use it for one session, a one-time session key. So let's talk about the operation of the KDC. Here's how it works. 1. When host A wishes to set up a connection with another host, it transmits a connection request packet to the KDC. Then the communication between A and the KDC is encrypted using a master key, which is shared only by A and KDC. So if the KDC has a whole bunch of hosts it communicates with, it's going to have a master key for each one of them separately. And then, number 2, if the KDC approves the connection request, it'll generate that unique one-time session key we talked about. And it's going to encrypt the session key using the permanent key, just like we talked about, which is shared with only A. So if B uses its permanent key, it's not going to be able to decrypt the session between the KDC and A. And then similarly, it will decrypt the session key by using the permanent key it shares with B, if B is going to be involved. So it's the KDC who communicates with each party with their own master key. And by the KDC having two separate independent encrypted sessions, one with A, one with B, it can distribute the keys to both of them. And then after it sends A and B the session key, then A and B can use the session key to communicate directly. So it all works as it should. So let's talk about Kerberos. And Kerberos is a key distribution and user authentication service. It was developed at MIT. So the problem that it's trying to solve is the following. Assume we have an open distributed environment in which users at workstations wish to access services on servers. And let's suppose those servers are all over the place. They're distributed throughout the network, or maybe even through the internet. Now we'd like for the servers to be able to restrict access to just the authorized users, and they should be able to authenticate requests for service. In this environment, a workstation cannot be trusted to identify its users correctly to network services. In particular, the following three threats exist. 1. A user may gain access to a particular workstation or PC and pretend to be another user operating from that workstation. 2. A user may alter the network address spoofing of the workstation so that the requests sent from the altered workstation appear to come from the impersonated workstation. So what a hacker does is spoofs the IP address of another user, and then the hacker wants to get onto the system. So we want to stop that as well. 3. A user may eavesdrop on exchanges and use a replay attack to gain entrance to a server or disrupt operations. And again, a replay attack, that's when we capture the traffic between two end systems, and then we send the same messages that were sent before. That's a replay attack. So in any of these three cases, an authorized user may be able to gain access to services and data that he or she is not authorized to access. So we're trying to solve that problem. Now, rather than building an elaborate authentication protocol at each server, Kerberos provides a centralized authentication server whose function is to authenticate users to servers and servers to users. That's mutual authentication. Now, Kerberos relies exclusively on symmetric encryption, making no use of public key encryption. So I'll put it in my own words. What we're doing is we have a whole bunch of clients, a whole bunch of servers, and instead of having every single server have the responsibility to do a great job of authenticating requests, what we do is we move all that functionality to one server, and then that one authentication server on behalf of the other 100 server is going to figure out if different communications are authorized or not, and then it's going to basically just tell the server, yeah, this we authorized this user to this user, or this user to this service, etc., etc. And then we don't have to have all the software on all those different machines. Now, you might not think it's like so fabulous to begin with, but one really nice thing about not having these services on 100 different machines is it may be like 100 different versions of a bunch of different operating systems. So we might have different versions of Linux, we might have some old mainframe, we might have some PCs running Windows, and even though we have different operating systems, we may have 5 different versions of each. And can you imagine how much work that is to try to maintain and have everything work perfectly? If we're going to have an authentication system on 100 different variations of operating systems and or versions. But if we can put it all on one system that really works rock solid for authentication services and Kerberos, then the problem becomes very, very simple. So it's actually a very elegant solution. So there's 2 versions of Kerberos which are in use, version 4, and those implementations still exist, but it's being phased out. Version 5 corrects some of the problems with version 4. And version 5 is actually an RFC as well, request for comment 4120. So because of the complexity of Kerberos, what we're going to do is talk about version 4 first. And then we're going to talk about version 5. So you're going to learn a little bit about Kerberos at a time. We're going to walk you through it, start at the beginning, and you'll learn one thing after another. And you'll also learn as we go through this, you'll learn what some of the weaknesses are in the older version, and then we'll talk about how the new version solved it. Okay, Now let's talk about version 4, as we said. Now version 4 makes use of DES in a rather elaborate protocol to provide the authentication service. So if we look at the Kerberos protocol as a whole, it's difficult to see the need for the many elements that's contained. But what we're going to do is we'll see different vulnerabilities, and then when we try to address those, you'll see why we have a fairly complex protocol, Kerberos. So what we're going to do is adopt a strategy which is used by many teachers, pedagogy. We start and teach you a few little things, and then we add upon that a little more, and we add upon that a little more, and it's much easier than trying to deal with 100 concepts at the same time. So here we go. So here's what we're going to do. Suppose, to begin with, we have an unprotected network environment. Any client can apply to any server for some kind of service. Maybe they want to get a file, they want to get a printer, whatever they want. They go to a server and get service. So we have some obvious security risks of impersonation. So one hacker may pretend to be an authorized user. So that's what they're going to do. The opponent or the hacker can pretend to be another client and obtain unauthorized privileges on server machines. So what are we going to do? We're going to counter this threat. So the servers must be able to confirm the identities of clients who request the service. We can't just trust them. So each server can be required to undertake this task for each client-server interaction. But in an open environment, this places a substantial burden on each server. Again, because we have a bunch of operating systems, we have a bunch of different versions, and even then, we have the server who has to communicate with all kinds of different clients, different operating systems and versions. So it is a tough one. What is the solution to that? Well, the alternative solution is to use an authentication server that knows the passwords of all users and stores them in a centralized database. In addition, the authentication server will share a unique secret key with each server. So there's not going to be one key with all servers. It's going to be a unique key with each server. So we got 10 servers, 10 keys. So these keys have been distributed physically or in some other secure manner. We'll just assume that. Okay, now although the foregoing scenario we just covered solves some of the problems with authentication in an open network environment, there are some problems that remain. Here are two particular problems. First, we would like to minimize the number of times that a user has to enter a password. Suppose each ticket can be used only once. If a user logs into a workstation in the morning and wishes to check his or her email at a mail server, they need to supply a password to get a ticket for the email server for access. And if they wish to check their mail several times during the day, each time they'll re-enter the password. And we don't want to make the user do that. So we can improve matters by saying that tickets are reusable. We can use them again and again. So for a single login session, we can go to the mail server after we get the ticket, and we can go multiple times to the server. And then we think, what kind of problems are we going to have if we do it this way? So if we do it this way, it remains the case that the user would need a new ticket for every different service. So if they wanted to go to a print server, a file server, and a mail server, they would have to log in 3 times, once for each service. So we'd like to avoid that. Another problem is that we were sending plain text transmissions of the password, and if the hacker gets that, they can see the password and then they can impersonate the user. So we definitely do not want to use plain text passwords. So to solve these additional problems, we're going to have a scheme for avoiding plain text passwords. And one way, of course, is to encrypt it, but there are other solutions which we'll talk about. And what we could do is have a new server called the ticket granting server. And that's all they do is grant tickets. This new service, they'll issue tickets to users who have been authenticated to the authentication server. So it's the authentication server that does the authentication, and then the ticket granting server will pass out these tickets, which will allow the users to access different services. So each time the user requires access to a different service, like email, database, the client will apply to the ticket granting server using the ticket to authenticate itself. So it's the TGS, ticket granting server, that will grant the ticket for the particular service, and the client will save these tickets and use them to authenticate to a different server each time a particular service is requested. So you should go ahead and hit pause, and you can look through and you can see the actual Kerberos protocol that is used. So this is a really nice diagram or figure. It shows you a simplified overview of the Kerberos, and I want you to go through each of those steps so you can see how they are performed. So go ahead and pause each time you need to. So this is a way we also describe protocols. This kind of we've got the different parties, and we've got the lines between some of them so we can see where the communication, we've got the arrows so we know which way the communication is going for each little piece of the session. So go ahead and go through that. Okay, and this introduced some justification for each of the elements in the protocol. You can read through those. And this is just part of the same table. You can see it's a very long table. And I don't think this is extremely complex, but it is time consuming to go through and read everything and understand it. I know that. And now we're going to talk about realms, Kerberos realms. So a full-service Kerberos environment consisting of a Kerberos server, number of clients, and applications requires the following. 1. The Kerberos server must have the user ID and hashed passwords of all participating users in its database. Notice it doesn't need the password. It's going to have a hashed password. And then all of the users are registered with the Kerberos server. 2. The Kerberos server must share a secret key with each server. All servers are registered with the Kerberos server. And such an environment that I just described is referred to as a Kerberos realm. The concept of realm can be explained as follows. A Kerberos realm is a set of managed nodes that share the same Kerberos database. The database resides on the Kerberos master computer system, which should be kept in a physically secure room. And if you want, you could have a read-only copy of the database on other Kerberos computer systems. However, all changes to the database should be made on the master computer system. Changing or accessing the contents of the Kerberos database requires the Kerberos master password, and that should be very private. Okay, well, let's talk about a principle, a Kerberos principle. So we have this related concept is that of a Kerberos principle, which is a service or a user that is known to the Kerberos system. Each Kerberos principle is identified by its principal name. A principal name consists of 3 parts: a service or a username, or an instance name, and also a realm name. Again, realm will tie it to the right database, and then we look in the database for the principal information. So networks of clients and servers under different administrative organizations typically constitute different realms. So different administrative organizations can each have their own Kerberos server database. So it's generally not practical and does not conform to good administrative policies to have users and servers in one administration domain registered with a Kerberos server elsewhere. However, users in one realm, again in one database, may need access to servers in other realms, and some servers may be willing to provide services to users from other realms. So you might have a server that's going to administer its services to two entirely different administrative domains. And we have to figure out how we're going to deal with those problems. Okay, now we're going to start talking about the differences between versions 4 and 5 of Kerberos. And it was version 5 that was intended to address the limitations of version 4 in two specific areas, what we call environmental shortcomings and then technical deficiencies. So we're going to summarize the improvements in each area. So the Kerberos version 4 did not fully address the need to be of general purpose, and this led to the following environmental shortcomings: encryption system dependence, internet protocol dependence, message byte ordering, ticket lifetime, authentication forwarding, inter-realm authentication. And apart from these environmental limitations, there are also technical deficiencies in the version 4 protocol itself. Most of these deficiencies were documented, and version 5 attempts to address all of them. The specific deficiencies are the following: double encryption, PC-BC encryption, session keys, password attacks. So here's a table which summarizes the basic version 5 dialog, and it's best explained by a comparison with version 4. That'll make it easier. Let's talk about key distribution again, but we're going to talk about it using asymmetric encryption. And before we talked about key distribution using symmetric encryption. So here's asymmetric now. Now on the face of it, the point of public key encryption is that the public key is of course public. Thus, if there is some broadly accepted public key algorithm, such as RSA, any participant can send his or her public key to any other participant, or they may wish to just broadcast the key to the community at large, maybe by putting it on a blog. Although this approach is convenient, it has a major weakness. Anyone can forge such a public announcement. That is, some user could pretend to be user A and send a public key to another participant or broadcast a public key. And until such time as user A discovers the forgery and alerts all the other participants, the forger is able to read all encrypted messages intended for A and can use the forged key for authentication. Well, that's the problem. What's the solution? So the solution to this problem is the public key certificate. In essence, a certificate consists of a public key plus a user ID of the key owner, with the whole block signed by a trusted third party. And typically the third party is a certificate authority that is trusted by the user community, such as maybe a governmental agency, a financial institution, and the user can present his or her public key to the authority in a secure manner and obtain a certificate. And then the user can publish the certificate instead of publishing their public key. Anyone needing the user's public key can obtain the certificate and verify that it is valid by way of the attached trusted signature. So we're going to have a diagram which is going to illustrate this soon on the next slide. Now, one scheme has become universally accepted for formatting public key certificates. It's the X.509 standard. And these X.509 certificates are used in most network security applications like IP security, secure sockets layer, SSL, S/MIME for email, and we'll talk about those later in the future chapters. So let's show you this diagram or figure, and this illustrates the generation of the public key certificate and shows you what's in it as well. Okay, let's talk about X.509 certificates. So it's the ITU-T recommendation X.509, and that's part of the X.500 series, that define a directory service. The directory is, in effect, a server or distributed set of servers that maintains a database of information about users. The information includes a mapping from username to network address, as well as other attributes, maybe like their email address. Now, the X.509 defines a framework for the provision of authentication services by the X500 directory to its users. The directory may serve as a repository of public key certificates. Each certificate contains the public key of a user and is signed with the private key of a trusted certification authority. In addition, X509 defines alternative authentication protocols based on the use of public key certificates. X509 is an important standard because the certificate structure and authentication protocols defined in X509 are used in a variety of contexts. For example, the certificate format is used in email, S/MIME, IP security, for when they're encrypting data between hosts, and SSL TLS, which is extremely popular for web browsers to be authenticated with servers. Now, X509 was initially issued in 1988, and the standard was revised to address some security concerns later. And then the third version was issued in 1995 and then revised in 2000. So it's been around a long time. X509 is based on the use of public key cryptography and digital signatures. The standard does not dictate the use of a specific algorithm, but recommends RSA. The digital signature scheme is assumed to require the use of a hash function. Again, the standard does not dictate a specific hash function. The 1988 recommendation included the description of a recommended hash algorithm. However, it was dropped because it wasn't very secure. So here's a figure showing the general format of a certificate. Okay, now it's the CA that signs the certificate with its private key. If the corresponding public key is known to a user, then that user can verify that a certificate was signed by the CA and that it's valid. So this is the typical digital signature approach, as illustrated in this figure. Okay, let's talk about obtaining a user's certificate. User certificates generated by a CA have the following characteristics. Any user with access to the public key of the CA can verify the user public key that was certified. No other party other than the certification authority can modify the certificate without this being detected. Because certificates are unforgeable, they can be placed in a directory without the need for the directory to make special efforts to protect them. If all users subscribe to the same CA, then there is a common trust to that CA. All user certificates can be placed in the directory for access by all users. In addition, a user can transmit his or her certificate directly to the other users. In either case, Once B is in possession of A's certificate, B has confidence that the message it encrypts with A's public key will be secure from eavesdropping, and that messages signed with A's private key are not forgeable. If there's a large community of users, it may not be practical for all users to subscribe to the same CA. Because it is the CA that signs certificates, each participating user must have a copy of the CA's own public key to verify signatures. This public key must be provided to each user in an absolutely secure way with respect to integrity and authenticity, so that users have confidence in the associated certificates. Thus, with many users, it may be more practical for there to be a number of CAs, each of which securely provides its public key to some fraction of the users. So what I did is I pulled up Firefox and I went into the options, and I'm showing you the certificate manager within Firefox, and we can see there's Microsoft here. I can click on this. It pulls up some details on a certificate. You can see who it's issued to, and these are the names the book talks about, CNOOU. So the CN common name is Microsoft Secure Server Authority. They've got the serial number the book talks about and everything, and you can just scroll down and you can go into details, and you can see that from Microsoft the next level up is GTE Cyber Trust Global Root, and that will be installed on PCs by default. So there you have it, an example. So this figure is taken from X509, and it's an example of a hierarchy. The connected circles indicate the hierarchy relationship among the CAs, just like I showed you before between the Microsoft and the GTE. And the associated boxes indicate certificates maintained in the directory for each CA. The directory entry for each CA includes two types of certificates: forward certificates, and they're certificates of X generated by other CAs, and reverse. So we have forward and reverse, and the reverse are certificates generated by X that are certificates of other CAs as well. Okay, let's talk about revocation of certificates. So remember before we talked about the certificate includes a period of validity, like a credit card when it's valid? Typically, a new certificate is issued just before the expiration of the old one. And also, we may wish on occasion to revoke a certificate before it expires for one of the following reasons. Let's suppose the user's private key is compromised. Then we would like to revoke the public key so it's no longer used. And another reason might be the user is no longer certified by the CA, maybe like the CA's regarding his work, and maybe the employee's employment has been terminated, so we'd like to revoke the certificate of that employee at that company. Maybe their name has changed, or for some reason the certificate is temporarily superseded, or the certificate was not issued properly. They want to revoke those too. So maybe the CA certificate has been compromised. That would be really bad, and that has happened. I remember with Komodo that happened. So each CA needs to maintain a list of all of the revoked but not yet expired certificates issued by that CA. And that's going to include both those issued to users and to other CAs. And the lists should be posted on its directory. Now, each certificate revocation list, CRL, posted to the directory is signed by the issuer and should include the issuer's name, the date the list was created, the date the next CRL is scheduled to be issued, and there should be an entry for each revoked certificate. Each entry consists of the serial number of a certificate and revocation date for that certificate. And because the serial numbers are always unique within the CA, the serial number is sufficient to identify the certificate. And when a user receives a certificate in a message, the user must determine whether the certificate has been revoked. It might have been revoked just like an hour ago. So the user could check the directory each time a certificate is received. And that might cause a little bit of a delay and cost. So to avoid the delays and costs with these searches, the user may have a local cache of certificates and lists of revoked certificates. Now that's a little bit of a problem, because if we have a cache and the cache is valid for, say, a month, what happens if we obtain a certificate, and remember, it's going to go in our cache for a month, but the next minute it's revoked and published sized as remote. If we have a cache for 30 days and we don't check for 30 days, we're going to be using a possibly fraudulent certificate. So those are the trade-offs between caching them and always double checking. Okay, well, let's talk about X509 version 3. So why do we have version 3? Well, version 2, that format does not convey all the information that recent design and implementation experience has shown is needed. So okay, let's talk about X509 and the different versions. And before we talk about version 3, let's talk about the limitations on version 2. So the version 2 format did not convey all the information that we would like to have. We came out with like a wish list when we were using version 2. And one of the issues or limitations with version 2 was the subject field. It was inadequate to convey the identity of a key owner to a public key user. And the 509 names in version 2 were relatively short, and they didn't have identification details that may be needed. Another issue, the subject field is also inadequate in version 2 for many applications. And these new applications want to recognize entities based on internet type things like email address, a URL, or some other internet related information. Also, there's a need to indicate which security policy is being referred to. This enables a security application or a function such as IPsec to relate an X509 certificate to a given security policy. Another version 2 limitation, there's a need to limit the damage that can result from a faulty or malicious CA by setting constraints on the applicability of a particular certificate. Also, it's important to be able to identify different keys used by the same owner at different times. And this feature supports key lifecycle management. In particular, the ability to update key pairs for users and CAs on a regular basis or under some kind of exceptional circumstances. So rather than continue to add fields to the version 2 fixed format, what happened is the standards developers felt that a more flexible approach was needed. So this version 3 includes a number of optional extensions that may be added to the version 2 format. And each of these extensions consists of an extension identifier and then a criticality indicator and an extension value. And the criticality indicator indicates whether an extension can be safely ignored. If it has the value of true and an implementation does not recognize the extension, it must treat the certificate as invalid. Now, the certificate extensions fall into three main categories: key and policy information, subject and issuer attributes, and certification path constraints. We'll talk about the key and policy information. Now, these extensions convey additional information about the subject and issuer keys, plus indicators of certificate policy. A certificate policy is a named set of rules that indicate the applicability of a certificate to a particular community and/or class of application with common security requirements. For example, a policy might be applicable to the authentication of electronic data interchange, EDI, transactions for the trading of goods within a given price range. This area includes the following: Authority Key Identifier identifies the public key to be used to verify the signature on this certificate or CRL. It enables distinct keys of the same CA to be differentiated. One use of this field is to handle CA key pairing updating. Subject Key Identifier identifies the public key being certified. It's useful for subject key pair updating. Also, a subject may have multiple key pairs and correspondingly different certificates for different purposes. They might have one digital certificate for a digital signature and another one for email, etc. Key usage indicates a restriction imposed as to the purposes for which and the policies under which the certified public key may be used. May indicate one or more of the following: digital signature, non-repudiation, key encryption, data encryption, key agreement, CA signature verification on certificates, and CA signature verification on CRLs. Now, the private key usage period, this indicates the period of use of the private key corresponding to the public key. Typically, the private key is used over a different period from the validity of the public key. For example, with digital signature keys, the usage period of the signing private key is typically shorter than that for verifying the key. Certificate policies. Certificates may be used in environments where multiple policies apply. This extension lists policies that the certificate is recognized as supporting, together with optional qualifier information. Policy mappings. Used only in certificates for CAs issued by other CAs. Policy mappings allow an issuing CA to indicate that one or more of the issuer's policies can be considered equivalent to another policy used in the subject CA's domain. Okay, let's talk about certificate subject and issuer attributes. These extensions support alternative names in alternative formats for a certificate subject or certificate issuer and can convey additional information about the certificate subject to increase the certificate user's confidence that the certificate subject is a particular person or entity. For example, information such as postal address, position within a corporation, or picture image may be required. The extension fields in this area include the following: subject alternative name contains one or more alternative names using any of a variety of forms. This field is important for supporting certain applications such as electronic mail, EDI, IPsec, which may employ their own name forms. Issuer alternative names contains one or more alternative names using any of a variety of forms. Subject directory attributes. These convey any desired X500 directory attribute values for the subject of this certificate. Certification path constraints. These extensions allow constraint specifications to be included in certificates issued for CAs by other CAs. The constraints may restrict the type of certificates that can be issued by the subject CA or that may occur subsequently in a certification chain. The extension fields in this area include the following: basic constraints. indicates if the subject may act as a CA. If so, a certification path length constraint may be specified. Name constraints indicates a namespace within which all subject names and subsequent certificates and a certification path must be located. Policy constraints specifies constraints that may require explicit certificate policy identification or inhibit policy mappings for the remainder of the certification path. And what will help you understand this material, I believe, is if you surf to Wikipedia, to this URL in the upper left, and you read their talk about X509, because their talk is a little bit more practical, and then it's easier to understand in a different way instead of just listening to the very high level description, if you can see how it's actually applied. So check that out and then continue. So RFC 4949, RFC again is request for comments, Internet Standards, is the Internet Security Glossary, and it defines public key infrastructure as the set of hardware, software, people, policies, and procedures needed to create, manage, store, distribute, and revoke digital certificates based on asymmetric cryptography. The principal objective for developing a PKI is to enable secure, convenient, and efficient acquisition of public keys. The Internet Engineering Task Force, IETF, Public Key Infrastructure, X509, working group has been the driving force behind setting up a formal and generic model based on X509 that is suitable for deploying a certificate-based architecture on the Internet. This section defines and describes the PKIX model. So the figure shows the interrelationship among the key elements of the PKIX model. And the different elements are the end entity, and that's a generic term used to denote end users, devices, servers, routers, or any kind of entity that can be identified in the subject field of a public key certificate. End entities typically consume and/or support PKI-related service. Certification authority, CA, that's the issuer of the certificates and usually certificate revocation lists. It may also support a variety of administrative functions, although these are often delegated to one or more registration authorities. And there's registration authorities, RAs, an optional component that can assume a number of administrative functions from the CA. So the RA is often associated with the end entity registration process, but can assist in a number of other areas as well. We have the CRL issuer, and that's an optional component that a CA can delegate to publish the CRLs. We have a repository, and that's a generic term used to denote any method for storing certificates and CRLs so that they can be retrieved by end entities. Okay, let's talk about the management functions. This architecture identifies a number of management functions that potentially need to be supported by management protocols, and they were indicated on the previous slide in the figure. But they include the following: registration. This is the process whereby the user first makes itself known to a CA prior to the CA issuing a certificate or certificates for that user. Registration begins the process of enrolling in a PKI. Registration usually involves some offline or online procedure for mutual authentication. Typically, the end entity is issued one or more shared secret keys used for subsequent authentication. Initialization. Before a client system can operate securely, it is necessary to install key materials that have the appropriate relationship with keys stored elsewhere in the infrastructure. For example, the client needs to be securely initialized with the public key and other assured information of the trusted CAs to be used in validating certification paths. Certification. This is the process where the CA issues a certificate for a user's public key and returns that certificate to the user's client system and/or posts that certificate in a repository. Key pair recovery. Key pairs can be used to support digital signature creation and verification, encryption and decryption, or both. When a key pair is used for encryption-decryption, it is important to provide a mechanism to recover the necessary decryption keys when normal access to the keyed material is no longer possible. Otherwise, it will not be possible to recover the encrypted data, and this is often done at companies. When an employee has different encryption keys to encrypt their information on their hard disk, etc., what would happen if that employee left the company or lost the keys or whatever? So we have this idea of like the custodian. The company is going to keep a copy of all of the employees' keys so that if something goes wrong, the company can recover it from a special place where they keep all the keys and that they don't lose all the data. Now, loss of access to the decryption key can result from forgotten passwords, PINs, corrupted disk drives, damage to hardware tokens, and so on. And key pair recovery allows end entities to restore their encryption-decryption key pair from an authorized key backup facility, typically the CA that issued the entity's certificate. Key pair update. All key pairs need to be updated regularly, replaced with a new key, and a new certificate issued. Update is required when the certificate lifetime expires and as a result of certificate revocation. Revocation request. An authorized person advises a CA of an abnormal situation requiring certificate revocation. Reasons for revocation include private key compromise, change in affiliation like when the employee quits the company, and name change. Cross certification. Two CAs exchange information used in establishing a cross certificate. A cross certificate is a certificate issued by one CA to another CA that contains a CA signature key used for issuing certificates. The PKIX working group has defined two alternative management protocols between entities that supports the management function listing in the preceding section. RFC 2510 defines the Certificate Management Protocols, CMP. Within CMP, each of the management functions is explicitly identified by specific protocol exchanges. CMP is designed to be a flexible protocol able to accommodate a variety of technical, operational, and business models. Well, we talked about RFCs, we talked about the IETF, so I wanted to show you. You can just surf to this URL and you'll go to the IETF. That's the Internet Engineering Task Force, and you can find all kinds of information. If you go here and you scroll down a little bit, I'll do that now. You can see RFC pages, and you can go ahead and go in there and you can look at RFCs and see, and that's a good way to get information in a different way. So when the book talks about RFCs, you might want to go check it out yourself. And it's the RFC 2797 that defines certificate management functions over CMS, and that's called CMC, where CMS refers to the RFC 2630 cryptographic message syntax. CMC is built on earlier work and is intended to leverage existing implementations. Although all of the PKIX functions are supported, the functions do not all map into specific protocol exchanges. So what I did is I went back to the IETF and I did a search, and I found RFC 2797, and I found something interesting. Look at this right here. Obsoleted by RFC 5272. And that's really handy. When you look at an RFC, if there's a newer one that came out, a new version that obsoleted the old one, where we shouldn't be working with the old one, it tells us. So what we should do is then jump over to RFC 5272. I just click on it and it throws me over there. And then if we scroll down, we can see an abstract. So we can get a very quick summary of the RFC. So that's a really good thing to do. As you read the book, you see RFCs, go in there, see if it's obsolete, look at the new one, look at the abstract, you get an idea of it. And if you want to get drilled down, get a little more technical, you can look at the exact RFC and get concise information. So let's talk some more about identity management. Now, federated identity management is a relatively new concept dealing with the use of a common identity management scheme across multiple enterprises and numerous applications and supporting many thousands, even millions of users. So we're going to begin our overview with a discussion of the concept of identity management, and then we'll examine federated identity management. Identity management is a centralized automated approach to provide enterprise-wide access to resources by employees and/or other authorized individuals. The focus of identity management is defining an identity for each user, human or process, associating attributes with the identity, and enforcing a means by which a user can verify identity. The central concept of an identity management system is the use of single sign-on, SSO. SSO enables a user to access all network resources after a single authentication. The following are principal elements of an identity management system. Authentication, confirmation that a user corresponds to the username provided. Authorization, granting access to specific services and/or resources based on the authentication. Accounting, a process for logging access and authorization. Provisioning, the enrollment of users in the system. Workflow automation, movement of data in a business process. Delegated administration, the use of role-based access control to grant permissions. Password synchronization, and I really like this one, creating a process for single sign-on or reduced sign-on. Single sign-on enables a user to access all network resources after a single authentication. RSO may involve multiple sign-ons, but requires less user effort than if each resource and service maintained its own authentication facility. Self-service password reset enables the user to modify his or her password. Federation, a process where authentication and permission will be passed on from one system to another, usually across multiple enterprises, thereby reducing the number of authentications needed by the user. Note that Kerberos contains a number of elements of an identity management system. This figure shows entities and data flows in a generic identity management architecture. A principal, again, is an identity holder. Typically, this is a human user that seeks access to resources and services on the network. However, user devices, agent processes, and server systems may also function as principals. It is the principals that authenticate themselves to an identity provider. The identity provider associates authentication information with a principal, as well as attributes and one or more identifiers. Increasingly, digital identities incorporate attributes other than simply an identifier and authentication information, such as passwords and biometric information. An attribute service manages the creation and maintenance of such attributes. For example, a user needs to provide a shipping address each time an order is placed at a new web merchant, and this information needs to be revised when the user moves. Identity management enables the user to provide this information once so that it is maintained in a single place and released to data consumers in accordance with authorization and privacy policy. So for example, you might have an account with Amazon.com and a whole bunch of other bookstores. You put in your address in all those places. But if you move and you want to have something shipped to a new place, you have to manually update a bunch of websites with that information. And this identity management service is the solution to that problem. Now, users may create some of the attributes to be associated with their digital identity, such as address. Administrators may also assign attributes to users, such as their roles, what are their access permissions, what is their employee information, for example, maybe their employee ID number. Data consumers are entities that obtain and employ data maintained and provided by identity and attribute providers, which are often used to support authorization decisions and to collect audit information. For example, a database server or file server is a data consumer that needs a client's credentials so as to know what access to provide to that client. So this figure illustrates entities and data flows in a generic federated identity management architecture. You can go read through those. Okay, let's talk about the standards. Federated identity management uses a number of standards as the building blocks for secure identity exchange across different domains or heterogeneous systems. And with these standards, we can make sure that if one vendor's product supports a standard and another's does, then we know they're going to interoperate together. If we didn't have standards, it would be extremely difficult to get different vendors' products to interoperate. So in essence, organizations issue some form of security ticket for their users that can be processed by cooperating partners. Identity federation standards are thus concerned with defining these tickets in terms of content and format, providing protocols for exchanging tickets, and performing a number of management tasks. These tasks include configuring systems to perform attribute transfers and identity mapping, and performing logging and auditing functions. The key standards are as follows. The Extensible Markup Language, XML. A markup language uses sets of embedded tags or labels to characterize text elements within a document so as to indicate their appearance, function, meaning, or context. XML documents appear to be similar to HTML. Hypertext markup language, documents that are visible as web pages, but provide greater functionality. XML includes strict definitions of the data type of each field, thus supporting database formats and semantics. XML provides encoding rules for commands that are used to transfer and update data objects. Now we're talking about XML, and of course it's interesting, how can you learn about XML? And let me share a secret with you. This w3schools.com is an awesome place to learn all kinds of things. You can learn XML, as we'll see, but you can learn HTML, CSS, you can learn JavaScript, you can learn server-side coding, and look at all these XML tutorials they have. And it's really a great site because not only do they talk about, for example, HTML and tell you how to code, but then you can type in little test code and you can click and then all of a sudden you can see the code rendered. So it's a fabulous place to learn all kinds of programming languages. They also have SQL, they have C#, just everything, including XML tutorials, which is what we're on. So go ahead and surf over there and check out the XML tutorials and everything else. Oh boy, look at this. To get some feel for the functionality of identity federation, we look at 3 different scenarios here. In the first scenario, workplace.com contracts with health.com to provide employee health benefits. An employee uses a web interface to sign on to workplace.com and goes through an authentication procedure there. This enables the employee to access authorized services and resources at workplace.com. When the employee clicks on a link to access health benefits, her browser is redirected to health.com. At the same time, the workplace.com software passes the user's identifier to health.com in a secure manner. The 2 organizations are part of a federation that cooperatively exchange user identifiers. It's health.com that manages user identities for every employee at workplace.com and associates with each identity health benefits information and access rights. In this example, the linkage between the 2 companies is based on account information, and user participation is browser-based. Now the figure B shows a second type of browser-based scheme. Parts supplier.com is a regular supplier of parts to workplace.com. In this case, a role-based access control RBAC scheme is used for access to information. An engineer of workplace.com authenticates at the employee portal at workplace.com and clicks on a link to access information at partssupplier.com. Because the user is authenticated in the role of an engineer, he or she is taken to the technical documentation and troubleshooting portion of Parts Supplier website without having to sign on. Similarly, an employee in a purchasing role signs on at workplace.com and is authorized in that role to place purchases at Parts Supplier without having to authenticate to Parts Supplier directly. For this scenario, Parts Supplier does not have identity information for individual employees at Workplace. Rather, the linkage between the 2 federated partners is in terms of roles. So let's move on to scenario C, and it can be referred to as document-based rather than browser-based. In this third example, Workplace has a purchasing agreement with Pin Supplies, and Pin Supplies has a business relationship with eShip.com. An employee of Workplace signs on, is authenticated to make purchases. The employee goes to a procurement application that provides a list of Workplace suppliers and the parts that can be ordered. The user clicks on Pin Supplies button and is presented with a purchase order web page. The employee fills out the form and clicks the Submit button. The procurement application generates an XML SOAP document that it inserts into the envelope body of an XML-based message. The procurement application then inserts the user credentials in the envelope header of the message together with Workplace's organizational identity. The procurement application posts a message to Pin Supplier's purchasing web service. The service authenticates the incoming message and processes the request. The purchasing web service then sends a SOAP message its shipping partner to fulfill the order. The message includes Pin Supplies security token in the envelope header and the list of items to be shipped, as well as the end user's shipping information in the envelope body. The shipping web service authenticates the request and processes the shipment order. Ooh, that was a lot. We're on to the summary page. So we talked about the symmetric key distribution using symmetric encryption. We talked about Kerberos and the different versions and why we need version 5. We then talked about key distribution using asymmetric encryption and that it has some advantages over doing key distribution with symmetric. We talked about the X.509 certificates, which are extremely popular, their features and functionality. We talked about the version 3. And then we talked about public key infrastructures. And then we tied it all together with federated identity management. And you can also think about when you log on to websites, sometimes they say, hey, you don't have to have a user ID password. You can authenticate with your Facebook credentials or your Google credentials. So we can see it coming on the internet, and pretty soon it's going to be everywhere. And we can reduce our long list of user ID passwords from 1,000, which is probably how many I have, to maybe at least 10 or 20. Okay, well, that's it for this chapter. Hope you enjoyed it. Bye for now.